Hi everyone, welcome once more to this YouTube channel. Today we're taking another content from general chemistry, which is a first year topic for students in tertiary or higher institution. And our discussion today will be based on the National University curriculum. We're going to look at types of chemical reactions. This is a follow-up to the topic we discussed or to the video we shot a few days ago on chemical equations. So this is a follow-up to that topic, a continuation of that topic. So if you are in high institution, first year precisely, or you are doing JUPEB program, JUPEB is Joint Universities Preliminary Education Board program meant for students that are intending undergraduates. So JUPEB program is something as first year curriculum, so that after JUPEB you can enter second year in Nigerian universities. So if you are watching us from diaspora, or that is from other countries, because our YouTube channel is global. So if you're watching us, this you're in high institution, this is also meant for you first year, or you are doing an A-level program, or you are in the 12th grade. So 12th grade refers to students in the final year of their high school, or what to call secondary school, down here. So this topic is also beneficial to you because this is the first year and high school are almost similar, apart from first year you move a little bit advanced compared to secondary school level. So if you are in this category that I mentioned, then you can join us. And then another thing we have to point out that if you're watching this video, you have to have your writing materials ready by your side, your note, your pen, or your jotter. This is not a movie that you're watching. So it's education or educational program. So you must have your materials and then put down whatever you're writing on the board, whatever you're teaching, and try to understand. You can also repeat the video and over again. You can also download it on your device, be it phone, tablet, or whatever you have, or laptop, and then enjoy the program. So this is your YouTube moderator, Dr. B. So today we're going to start with types of chemical reactions. We know that in the previous video, when we did chemical equation, we defined chemical reaction as a process by which one or more substances known as reactants are transformed or changed into new substances known as products. So that will define a chemical reaction. In fact, chemical reaction is synonymous to chemical change, a process by which one or more substances known as reactants are transformed into new substance known as product. And we say that in chemical reactions, we try to represent chemical reactions symbolically. So when we now represent what is happening in chemical reaction using chemical symbols or chemical formula, symbolically we now have what we call chemical equation. For instance, we'll have A plus B giving us C plus D. So this is a hypothetical example of what is meant by a chemical equation, where capital A and B are the reactants, capital C and D are the products, small a and small b are the coefficients of the reactants, which we call the stoichiometric number of moles. Small c and small d are the coefficients of the products, which refers to the number of moles of the product as it appears in a balanced equation. Now, before we go to the types of chemical reaction, we have to complete what is remaining of the previous video. We're going to look at information provided by a chemical equation. What information can we get from a balanced chemical equation? So we'll now look at that briefly. So on the whiteboard, we have informations that we can obtain from a balanced equation. The first information a balanced equation can provide is conservation of mass. So what does it mean? The balanced equation here would say it shows that the number of atoms of each element is the same on both sides. I repeat, it shows conservation of mass. It shows that the number of atoms of each element is the same on both sides. So what it means, or indirectly, is that a balanced equation shows the number of atoms present in the reactant and also present in the product, and also it tries to conserve mass. Look at this example below. You look at, if you count, hydrogen atom in this acid is 2 atoms, while in this base 2 times 1 gives you 2. So 2 of hydrogen here plus this 2, that is 4. If I go to that side, 2 multiplied by 2 is 4. So hydrogen is balanced, equal number. Then sulfur is 1 atom here, and then 1 atom there, balanced. Oxygen is 4 here. 2 times 1 here is 2. So 2 plus 4 is 6. On the other side, 4. 2 times 1 oxygen here is 2. 2 plus 4, 6. So oxygen is also balanced. Going to sodium. 2 times 1 here is 2. So 2 of sodium, and also here 2 of sodium. So you see that this equation is balanced, showing the number of atoms on both sides of the equation. Number of atoms of reactants and number of atoms of the product, showing that they are equal to each other. So that means a balanced equation conserves mass. Number 2 information you can get for a balanced equation is mole ratios. I read mole ratio. The coefficient on the balanced equation gives the exact mole ratios of reactants and products. Mole ratio, explanation. The coefficient on the balanced equation gives the exact mole ratios of reactants and products. That is to say that a balanced equation provides the mole ratios of reactants and products. So coefficients mean the number standing in front of a substance. Like this acid, it appears you're seeing nothing in front, but there's something in front. That thing in front is 1. Without anything in front means 1. Why this one? This base, the number in front, the equation is 2. For this salt, the equation is 1. While water, the equation is 2. So I can interpret this equation. I can say 1 mole of H2SO4 reacted with 2 moles of NaOH to produce 1 mole of this and 2 moles of that. So we can say this is 1 mole for this acid. The equation is 1, 2 moles for this, then 1 mole for that, and 2 moles for that. So the mole ratio is 1:2 for the reactants and 1:2 also for the product. So it gives the mole ratio of the reactants and product in a balanced equation. So the mole ratios are the coefficients we are seeing. So that we can get for a balanced equation. Number 2 information you can get. Number 3 is quantitative relationship. Quantitative relationship. From the mole ratio we have here, we can determine how much of the reactants are involved or products formed. That is when you go to a topic called stoichiometry of reactions or do some calculations. So from the mole ratio, we can calculate how much of the reactant that is involved, or which of the reactant is necessary, or which of them is limiting. We can still calculate how much of the product that is being formed. That is what is meant by quantitative relationship. Then number 4 information that a chemical equation provides is what's called the physical state. Physical state, yes. Although it's not necessary that you should put it, but it's very important that the chemical equation should also provide physical state. So in a balanced equation, sometimes or often we see letters like L in bracket. L implies liquid, like water. G, which implies gas. AQ, which implies aqueous. Aqueous means substance dissolved inside water. Then S, which implies solid or insoluble substance. I repeat, L stands for liquid, G, gas, AQ, aqueous or dissolved, soluble in water, then S, insoluble in water or solid. So the chemical equation is often accompanied by these 3 terms. For instance, in this one on the board, I can put this instance or this example, like this is an acid. An acid is always soluble in water, because in some water I'll put AQ meaning aqueous. This is a base, alkali, and alkalis are solid water. I put AQ meaning it dissolves inside water. This is sodium salt. Sodium salts are normally solid in water. I put AQ meaning aqueous. This is water. I put L meaning liquid. So you can see that. So I can say have another example. I have CaCO3 plus HCl giving us CaCl2 plus water plus CO2. So this is an equation. So I can still bring in these subscripts here. So this substance is calcium carbonate limestone, and limestone is insoluble in water. So because it's insoluble, I write S, solid. Acids are soluble, aqueous. This salt is a soluble salt, I put aqueous, AQ. Water, I put liquid. And then CO2, I put, is a gas, I put G. So it's not mandatory that you must put all these things, but when you want to put it, make sure that what you're putting is correct. Because if you go and write L for an insoluble salt or put gas for a salt, is totally wrong. If you write it without putting this information there, it is not wrong. But if you want to put the information L, G, their physical states or their different phases, make sure they are all correct phases that you are putting. That is physical state. Number 5 is reaction conditions. Some chemical reactions provide the conditions meant for the reaction. These conditions can be pressure, could be temperature, or concentration. So that are the reaction conditions. For instance, I can have a reaction of this nature. Let me say S2 plus Y2, and then maybe we add the gases, and I write 2SY produce. And here you see it's something like 180 degrees Celsius, 1.5 atm. So what does it mean? All these things written on top of the arrow are the reaction conditions. It means this reaction occurred at 180 degrees Celsius and then at a pressure of, since we have gases, of 1.5 atmosphere. So these are the information that you can gather or can get from a balanced chemical equation. So now we're going to information that a chemical equation cannot provide. Information that chemical equation cannot provide or we cannot get from a balanced equation. Okay, on the whiteboard we have information that cannot be obtained from a balance or from a chemical equation. The first is reaction mechanism. So what is the reaction mechanism? We say this is the step-by-step process by which reactants are transformed into products. So a balanced equation does not provide reaction mechanism. A balanced equation is just a summary of the reaction process that are taking place. So many reactions you see in chemistry, when you have an equation written for you, it does not mean that equation you are seeing is the summary of the overall summary of all the reactions that are taking place. So a reaction can take place in different steps. These different elementary steps make up what we call the reaction mechanism. So the balanced equation does not provide these small steps that leads to the overall equation. So if you want to know the reaction mechanism of a particular reaction, a different topic, which is a chemical kinetics, provides information about reaction mechanism, not a balanced equation. Number 2 is rate of reaction. A balanced equation does not provide information about the rate of reaction or about the speed by which a reaction takes place. So a balanced equation does not tell us the rate of reaction, the rate at which the reactants are consumed, or the rate at which the products are formed. No. Number 3, energy changes. Energy changes, we cannot get information about energy changes from a balanced equation. I said it does not give information about the enthalpy change, delta H, entropy S, or gives free energy, delta G. So we cannot get these information from a balanced equation. To study this in detail, we refer to a branch of chemistry called chemical thermodynamics. So this cannot be obtained from a balanced equation. Number 4, form of products. This is with respect to organic chemistry, isomerism. A balanced equation does not actually indicate the form of the product. For instance, we may have a reaction between maybe butene and chlorine molecule. When butene and chlorine molecule react, we may have a product like, let's say, butene, a product like 2,3-dichlorobutane. So, or someone might feel that it could be 2,3-dichlorobutane. So, other person may feel that it may be 2,2-dichlorobutane or 3,3-dichloromethane. Which of them is the correct form? You cannot get it for a balanced equation unless you start moving into structural formulas. Number 5, concentration or amount of reactants and products. Yes, even though the balanced equation provides the coefficients of reactants and products, that is the number of moles of reactants and products as it appears in the balanced equation, are the coefficients which we explained earlier on, but it does not tell us the actual amount of the reactant involved in the reaction or the amount of product formed in the reaction. We cannot get that from a balanced equation. Number 6, side reactions. Some reactions are accompanied by side reactions, which is not presented in the main balanced equation. Number 7, the balanced equation does not tell us whether the reaction goes to completion or reaches equilibrium. We cannot get this information from a balanced equation. Then number 8, feasibility of the reaction or spontaneity of the reaction. Feasible means, when we say reaction is feasible, it means that the reaction can take place. So, when we say it's feasible, it means it can take place. For instance, let's look at this example here. Zinc plus copper sulfate. We have zinc sulfate plus copper. Or copper plus zinc sulfate. We have copper sulfate plus zinc. So look at the two equations. So look at them. In this one, zinc displays copper. In this one, copper displays zinc. So you can see the difference. So these two reactions are balanced equations. If you look at them very well, the atoms are all balanced on both sides. But one of the reactions we're seeing on the board is not feasible, cannot take place. Cannot take place. It's only one of them can take place. The one that can take place is the first equation. Yes, but this second one cannot take place. So even though it's a balanced equation, but it doesn't tell us whether it can take place or not. So why this one can take place? Because zinc is more electropositive than copper. That's why zinc can displace copper to give us this product. In this one, copper is less electropositive than zinc. So copper cannot displace zinc. That means we are not even supposed to have any product. There shouldn't be any reaction here, even though it's balanced. So that could be misleading. So a balanced equation does not tell us whether the reaction can take place or not. So when you say balanced equation, it doesn't mean that actually what you're seeing can take place. So that is it. So these are the information that we cannot obtain from a balanced equation. Now, we're now going to what we have today, which is types of chemical reaction. So on the whiteboard, we have the types of chemical reactions. In this our lecture or tutorial, our focus will be on the types of on inorganic reactions, not organic reactions. So that's general chemistry for first year students and JUPEB program and A-level students, and also high school, final year, etc. students. So the types of chemical reactions we have in inorganic chemistry include: number 1, combination or synthesis reaction; number 2, decomposition reaction; number 3, single displacement or single replacement reaction. So either you call it displacement or replacement. Number 4, combustion reaction. Number 5, dehydration reaction. Number 6, double displacement or double replacement reaction. So look at number 3 and number 6. Single displacement or replacement for number 3. Number 6, double displacement or replacement. They are two different things. Then number 7, redox reactions. So these are the major 7 types of chemical reactions we encounter in inorganic chemistry. So we're going to discuss them one after the other and give examples of these kind of reactions. So the first one we have on the board is combination reaction, otherwise called synthesis reaction. So in combination reaction, combination or synthesis reaction, two or more simpler substances combine to form a single complex product or substance. So you see, the characteristics or the uniqueness of combination reaction is that the reaction must involve two or more reactants, but you only have one product. That is combination reaction. It could involve element and another element, giving us a compound. Element like iron plus sulfur, giving us iron 2 sulfide. You can see that. Two elements or two reactants and one product. It could involve molecule plus another molecule, giving us compound. For example, hydrogen plus chlorine, giving us HCl. Two molecules and one compound. You see, the uniqueness here is that you can have two or more reactants, but you will only have one product. I look at it very well. You see that the product, if you split it, you have the reactants. Like the product contains iron and sulfur. HCl contains hydrogen and the chlorine. That is combination reaction. Either call it direct combination or you can call it synthesis reaction. Synthesis. Iron sulfide is synthesized from its elements. HCl is synthesized or produced from its elements. That's what is meant by combination reaction. You can still have a situation whereby we have maybe two smaller compounds. Two smaller compounds to give us a bigger compound. That is also combination reaction. A bigger compound. For example, calcium oxide reacting with sand or silica, giving us a bigger compound, calcium silicate or triazosilicate. So what do we observe in all of them? In all these instances we are provided above, you see that you are having two reactants, or could be more than two reactants, but the unique thing there is must have one product. We call such a reaction combination reaction or synthesis reaction. So we go to reaction number 2, which is decomposition reaction. So we have number 2 reaction called decomposition reaction. So this reaction is opposite of combination reaction. You might say about combination synthesis reaction, we have two or more reactants combining to give us only one product. So however, in decomposition reaction, one reactant splits into two or more products. It's the opposite of synthesis reaction. In synthesis, two or more reactants forms one product, while in decomposition, one product splits to give you two or more. One reactant splits to give us two or more products. So in this reaction, a complex substance or compound, which is the reactant, splits in the presence of either light, electricity, or heat to produce two or more products. So you can see that decomposition is opposite of combination reaction. So, for instance, I have this compound SYZ. Perhaps heating it can split into perhaps SZ and perhaps YZ. So a compound splits into two major components. So in decomposition reaction, you only have one reactant, but two or more products. But if I should turn it the other way around and put this one on the left hand side, right hand, and put this one as the product, it now becomes combination reaction or synthesis reaction. So looking at this now, for this substance to split, there should be a kind of initiator or agent that can cause it to split. That agent can be UV, ultraviolet radiation, that is light, can be electricity, or can be heat, which can be signified sometimes with a triangle, meaning heat. So these are the initiators or the agents that can cause a substance to split. So we'll now look at the different kinds of combination reaction, decomposition reaction. That means there are three types of decomposition reaction. We have what we call photochemical decomposition, when it is facilitated by light. We have electrolytic decomposition, when the agent causing it to decompose is electricity. We have thermal decomposition, when the substance decomposes, because the word thermal means heat. So there are three types of decomposition reactions we recognize in chemistry. So depending on what brought about the actual or the agent or the initiator that caused the substance to decompose. If it's light or UV rays, we call it photochemical decomposition. If it's electricity, we call it electrolytic decomposition. If it's heat, we call it thermal decomposition. So we're going to look at these three types of decomposition reaction one by one briefly. So let's go to photochemical decomposition. I'll give an example. So photochemical decomposition. So this occurs when a compound decomposes into two or more products in the presence of light. So that is the first example of, or the first type of decomposition reaction, called photochemical decomposition reaction, brought about by sunlight. So an example of this kind of decomposition is decomposition of a compound called hydrogen peroxide. This compound is light sensitive, very sensitive to sunlight, so sunlight can easily decompose it. So when it's exposed to sunlight, it splits into water plus oxygen. So to balance the equation, we have learned equation balancing, so can balance it without waste of time. So you have that. And then to show that sunlight facilitated the reaction, I'll put maybe UV or light above the arrow. So this is an example of photochemical decomposition reaction. And then we can still have silver nitrate or silver compounds that are decomposed by sunlight. Silver nitrate split into silver, a gas called nitrogen 4 oxide, and a gas called oxygen gas when exposed to sunlight. So we can have balance it by putting 2 here, putting 2 there, and then of course putting 2 there. So that becomes balance. Then we can still have maybe silver chloride. Silver compounds are always light sensitive, splitting into silver and releasing chlorine gas. You have 2 here, you put 2 balance this, and then put 2 here. So these are few examples of photochemical decomposition reaction, which is facilitated by light. We can still call them photolytic reactions, photolytic decomposition reaction, or photochemical decomposition reaction. So the next type of decomposition reaction, which I mentioned here, is electrolytic decomposition reaction, which is also indirectly known as electrolysis. So electrolytic decomposition reaction, whereby electric current is passed through a substance, causing it to decompose. So that is it. An example is water, electrolytic decomposition of water. So is the chemical decomposition of a substance by passage of of electric current or electricity through it. So this is the second type of decomposition reaction. Like water can split when you pass current to it. Water can split into these components, which is hydrogen and oxygen. So this could be caused by electrolysis or by electrolytic decomposition reaction. So that is the second type of decomposition reaction. Then the third type is the one facilitated by heat or thermal energy, called thermal decomposition reaction, which is the more common type of the decomposition reaction. So we say this is the decomposition of a complex substance or of a compound into two or more products in the presence of heat energy. So we'll call this thermal decomposition reaction. For example, when we heat limestone, or when we heat metals, carbonate, this is a carbonate, CO3 refers to carbonate, or triisocarbonate, or divalent metal. Divalent means metals whose valency is 2. Decompose, let me give you a general form. MCO3. This M stands for a metal whose valency is 2. When you heat their carbonate, they break down into their oxide and release CO2. So where M is the divalent metal of a carbonate. So when you heat the carbonate of metals, they break down into the oxide and carbon 4 oxide. So an example of divalent metals are metals of group 2 elements. The group 2 elements are divalent. Group 2 metals include calcium, magnesium, barium. These are group 2. So I can put calcium here, CaCO3. It will now give me calcium oxide and CO2. Magnesium there, magnesium carbonate, magnesium oxide and CO2. Barium carbonate gives me barium oxide and CO2. So you have to master these rules. So there are rules guiding the composition, because this reaction is very difficult to predict the product. But if you master the rules as I'm listing them, then you can be able to know what is formed when a particular salt is decomposed. So divalent metal of a metal salts, divalent metals, metallic salts of a carbonate decompose. So example of divalent metals are group 2 metals, elements in group 2. But you should know that the group 2 elements are not only the divalent metal. There are some metals that are not in group 2 that are divalent. Also like zinc. Zinc is in the D block. The valence is 2. So zinc, when you heat zinc carbonate, it will still decompose in this form. Zinc oxide and CO2. Another divalent metal we encounter is copper. Copper can see its valency of 2. Give you copper oxide and CO2. So you can see this. This is the rule guiding carbonates. How the carbonate decompose. So divalent carbonates, or carbonates in which the metal in them is have a valency of 2, break down into their oxide and releasing carbon 4 oxide. Then, what are the carbonates of group 1 metals? Group 1 metals are elements metal like sodium, potassium, rubidium, francium, and cesium. Group 1 metals. So they are carbonates. So the carbonates of group 1 metals do not decompose on heating. So they are stable to heat. So if I heat sodium carbonate from now to tomorrow, there will be no product, because the bond between this sodium and the carbon is very strong. They are highly electropositive, so it will not let go of carbon nor oxygen. If I heat potassium carbonate from now to tomorrow, there will be no product. So if I heat rubidium carbonate, all the group 1 carbonates, they do not break down. But those of group 2 and divalent metals, their carbonates give you the oxide and CO2. Okay, There's one group 1 metal I did not mention here is lithium. It's not listed here. Lithium is an exemption to this rule. Among the group 1 carbonates, lithium carbonate decomposes. Lithium decomposes. Why? Because lithium, even though it's in group 1, lithium has a diagonal relationship with magnesium, which is in group 2. So in the periodic table, among the first 20 elements, the element that have diagonal relationship is this similar property. So you go to your periodic table, look at the position of lithium group 1, and then move it diagonally, draw a line across in diagonal manner. You're going to move from lithium to magnesium. And magnesium is in group 2. So because lithium has a diagonal relationship with magnesium, that's why lithium can behave like group 2 metal, they're carbonates. So when you hit lithium carbonate, it breaks down. So that's the only group 1 metal whose carbonate can decompose like group 2, while the other group 1 carbonates cannot decompose. So having done that, what of the nitrates? Nitrates refers to triosonitrates. Triosonitrate salts. Nitrate 5 salts. That's NO3. Called the nitrates. So when you join a metal to them, you now form a salt. So the group 1 nitrates, group 1 triosonitrates decompose on heating to their diazonitrates, nitrate 3, and release oxygen. So if I put a group 1 metal here to form a salt, like sodium, I have NaNO3, sodium triazonitrate 5. If I heat it, this is tri, also. You're going to give it the diazo. That is remove 1, that is 2. Remove 1 oxygen, you have NaNO2, diazonitrate. So from triazo to diazo, removing, abstracting 1 oxygen here, and I'll give you that. And then releasing oxygen gas. As a gas becomes O2 as a molecule. So you see the way it behaves. Balancing the equation, you need to put 2 here and put 2 here. It should be a balancing. Then if I hit potassium trionitrate, it's also a group 1 metal, I'll get potassium diazonitrate, it's similar to this one, and then also oxygen gas. So this is how the group 1 nitrates behave. When you hit group 1 nitrates, they decompose into their diazonitrate, and at the same time, they release oxygen gas. Then what of group 2 diazonitrate? So the group 2 metals. Group 2 trionitrate or decompose to their oxides, releasing 2 gases. 2 gases include a brown gas called nitrogen 4 oxide and oxygen gas. They give 3 products. So you can see the differences. So having done that, for example, calcium is in group 2, NO3. You should know why there is 2 here. Valency change. When you combine calcium and NO3, the valence of calcium is 2, NO3 is 1. So when you change, the 2 goes to NO3 and the 1 goes to calcium. That's why the formula is like this. So when you hit a group 2 nitrate, you're going to decompose, give you the oxide, as we said, the oxide, calcium oxide, then these 2 gases, NO2 and oxygen. You see that? You can balance it. You have learned how to balance the equation with me in that previous video. You can check it yourself. Then if I use magnesium, also in group 2 metal, similar decomposition, magnesium oxide, NO2 as well as oxygen. So you can balance it, 2, 2, and then 4. So remember I told that group 2 metals behave in a similar way. They are sourced like other divalent metals that are not in group 2. I gave you other divalent metals like copper. So if it's copper, valency is 2 in this case. It will still decompose in the same manner. Copper oxide, NO2, and then oxygen in a similar fashion. If I use lead, valency is 2 here, divalent, lead oxide, NO2, and even if I use zinc nitrate, similar fashion, this similar products, you are going to observe. So you see the way group 2 divalent nitrates, that is, or divalent nitrates decompose, different from the group 1 nitrates that give you their diazonitrate and oxygen gas. So the third kind of salt we want to look at are the hydrogen carbonates. Hydrogen carbonates, the salts that carry the ion, hydrogen triioxocarbonates, you can call them bicarbonates. Carbonates have this is the radical. When you join it to a metal, you now form the salt. Any metal decompose into carbonates, CO2 and water. It does not matter the metal that is there. If it's a group 1 metal, that is MHC, it look like this. But group 1 metals have valency of 1. Here it should be 1. While this one is 1, negative 1. So equal valency cancel out. Nothing is a change. So formula will look like this. Like sodium hydrogen carbonate. So when you heat it, it's going to give you the carbonate. That is M2CO3, water, and CO2. For instance, this one gives you sodium carbonate, water, and CO2. You should know why we have 2 here. The valency of sodium is 1. The valency of carbonate, tricarbonate, is 2. When you change, the 2 comes there. That's why the formula is correct. But this one, hydrogen carbonate is different from carbonate. Hydrogen carbonate have valency of 1, while carbonate have valency of 2. So you can balance it by putting 2 there. So that is it. Then if you use a group 2 metal in place of this, let me say calcium, combined with the hydrogen carbonate, the formula, is it right? Looking at this is not right because the valency of calcium is 2, the one is 1. So when you change to form the formula, the 2 from the calcium will not be achieved. The Y1 will give into calcium. So these are the right formula. It will not look like that of group 1. When you heat it, you're going to still provide similar product like that of group 1 metal. That is the carbonate, calcium carbonate, water, and also CO2. So it is in the hydrogen carbonates that the group 1 source and the group 2 source produce similar kind of products. The only difference is the way you write their formula. So you see that. So carbonates of group 1 and carbonates of group 2 produce similar product. Hydrogen carbonates of group 1 and that of group 2 produce similar products. So which are the carbonates, water, and carbon 4 oxide. So these rules, you have to master them to do well in this aspect of decomposition called thermal decomposition. Then what of metallic oxides? Do metallic oxides decompose? Metallic oxides of highly electropositive metal like sodium oxide, calcium oxide, magnesium oxide, zinc oxides, these ones don't decompose when heated. But metallic oxides of low reactivity metal, low electropositive metal like silver, mercury, gold, this one, the oxides can decompose because the metals are very low in reactivity. Like the valency of silver is 1. To form silver oxide, have AgO, Ag2O, because silver is B valency of 1, also is B minus 2. Right formula, when you combine, you change in valency, you have 2, you have 1 there. Is the right formula. So you have to be very careful of formula in chemistry or chemical reactions. Don't use the wrong formula. So when you heat silver oxide, you're going to give us silver and release oxygen. You decompose the metal and give you oxygen gas. Because, okay, balance, this is 2, 2, oxygen is 2. How to put 2 here? To make oxygen 2, silver now becomes 4. So you can see that. So when you heat oxides of these metals, they decompose to give you the metal and the release oxygen. Mercury, 2 oxide. Mercury here have valency of 2, oxygen has 2. So equal valency cancel out. You join, nothing will change. So you now have mercury oxide and mercury and oxygen. You can balance it up on your own. Likewise, gold oxide. So when you heat oxides of such metals, they decompose. But when you heat oxides of highly reactive metals, potassium, sodium, calcium, aluminum, magnesium, zinc, lead, copper, these oxides are stable. When you heat them, they cannot decompose because the any bond there is very strong. but these ones are less reactive metals, so the oxides can decompose. So having done that, we're going to the next type of reaction called single displacement reaction. In single displacement reaction, an element displaces another element from its compound. So say in this reaction, an element displaces another element from its compound, or from an aqueous solution of its compound. An element displaces another element from its compound. That is single displacement. An element comes into a compound to displace another element. For instance, I may have S, an element, plus a compound YZ. So S, being more reactive than Y, goes on to displace Y and take its position. Now I have SZ and then Y coming out to take S position. So we call this single displacement reaction. So in this reaction, a more reactive or positive metal, or you can say cation. Cation means metallic ion or positive ion, displaces a less reactive metal or cation from its source. A metal displaces another metal, while a more reactive non-metal, which we can call anion, negative or negative ion, displaces a less reactive non-metal or anion. Anion refers to negative ion. So you see that. So for this reaction to take place, it must be an element displacing another element. Does it mean that every element can displace another element? No. An element can displace an element that it is stronger than. So a weaker element cannot displace a stronger one. So if S should displace Y, that means S is more reactive than Y. But if S is less reactive than Y, there will be no reaction. So let me give you examples of these kind of reactions. So we have on the board, we have zinc plus copper sulfate. So we have zinc sulfate plus copper. An example, copper plus silver nitrate, giving us copper nitrate plus silver. So number 3 example, you have chlorine gas plus sodium bromide, giving us sodium chloride. Have this plus bromine. And example, we have bromine plus sodium iodide, giving us sodium bromide plus iodine. So look at these examples. Also another one, zinc plus HCl, zinc chloride plus hydrogen gas. So let's take some few minutes to go through these displacement reactions. The first one, if you look at it very well, zinc plus copper sulfate. Zinc had displaced, look at the product. Zinc had replaced the position of copper. That's why it's called single displacement, or you can say call it single replacement. A metal come to take place of another metal in its compound. Give you why? You can see that zinc was formerly solid. But when it enters into copper position, it dissolves and becomes aqueous in solution. While the copper that was dissolved before will now come out as solid. Take the state of zinc. You can see that. In this situation, copper, look at the product. Copper had displaced silver. So you can see that. Copper being solid, on the place silver dissolve and become aqueous. While the silver that was dissolved before comes out as a solid. So in this other one, this two example shows metals displacing their fellow metals. While this other one shows a non-metal displacing. See, that's why I say that a metal will displace a metal, or a more reactive metal will displace a less reactive metal, while a more reactive non-metal will displace its fellow non-metal. So chlorine could not displace sodium because sodium is a metal. So chlorine will only displace bromine, its fellow halogen or non-metal, giving you this and that. So in this one, bromine displays iodine, giving you this and iodine coming out. In this other one, zinc is a metal, hydrogen is a non-metal, but zinc appears to have displaced a non-metal, which is hydrogen. Why? Because hydrogen is with electropositive character, like metals. So that is why zinc displays the more electropositive here, which is hydrogen. I'm giving you that hydrogen now comes out as a gas. So these are the examples of simple single displacement reactions which are feasible or which can take place. How do you know whether the reaction can take place or not? How do you know metals that are more electropositive than the others? So that will take me to our activity series. That will help you as a student to know that. We have the activity series for cations. Cation is referred to positive ions. We have anions. So cations have this with their charges. Okay. So that is it. So this series shows the metals, the common metals for their reactivity. As you go down, the reactivity decreases. The most reactive is potassium, followed by sodium, followed by calcium, and the least here is AU. Good. So you can memorize it with a mnemonics. Mnemonics is the kind of short, funny poem. You can use here. I can say, please stop calling me a zebra. Instead, tell there's lead here before hydrogen. Instead, tell Laura how copper helps silver to strengthen gold. So you can see a very simple thing. Please stop calling me a zebra. Instead, tell Laura how copper helps silver to strengthen gold. So you look at the mnemonics, P stands for potassium. So another symbol from kalium, Latin word, potassium, that is K. Stop, S stands for sodium. The symbol is Na, natrium, Latin word. So some of these mnemonics using their English names, or third letter for the English names. C or Ca stand for calcium. M stand for magnesium. A stand for aluminium. Z stand for zebra. I stand for Fe, means iron, ferrium, iron. T stand for tin. Sn, the symbol of tungstanium. L stand for lead. B, the symbol of lead, from plumbium, Latin name, lead. Lead, and lead. So I call it lead. Depending how you pronounce it. H stand for hydrogen. How? Copper. You use the full name for this one, copper. Then H here stand for mercury. Mercury symbol is Hg, hydradium. Mercury is Hg. Then silver, Si, silver. So that we use the full name of this element. So we use full name for we use the full name of elements for copper, mercury, copper. Sorry, they come again for copper, silver, and gold. This is where we use the actual names. So this is mercury, silver. Then to make it stand funny when I say to strengthen gold. Gold is AU from the word arium. Now, how does this help us to predict? Let's look at these reactions and see which of these reactions are feasible or can take place as in chemistry. Which of them can take place as displacement reactions in chemistry? So that could be a question. So, let's see. Can these reactions take place? Let's find out. From our electrochemical series of this is for cations or positive ions. See that they're all metals, positively charged. The only one that's not a metal here is found here is hydrogen. Others are the common metals. So let's see. Verify that. Then we also have zinc plus sodium chloride. Zinc chloride. So which of these reactions are feasible? In chemistry, when we say reaction is feasible or spontaneous, it means it can take place. But when we say it's non-feasible or non-spontaneous, it means that it cannot take place. Look at the first reaction. Copper displays, zinc displays copper. Is it possible? Yes. Because look at zinc. Zinc is higher than copper. It's more reactive than copper. So zinc can displace copper. So this is feasible, can take place. The second reaction, look at copper. Copper displays magnesium. Look at where you have copper. Look at magnesium. Magnesium is more reactive than copper. So this reaction cannot take place, not because this is less reactive. Look at the position. Look at this one is higher. So copper cannot displace magnesium. Look at the third one, iron and hydrogen. Where is iron? Look at iron position. Then look at hydrogen. Iron is higher than hydrogen. So this reaction is feasible, can take place. Look at the third one, zinc displacing sodium. Is that possible? Where is zinc? Look at zinc position and look at sodium. Sodium is more active than zinc. So zinc cannot displace a stronger metal. So this is not possible, not feasible. So you can see how you check it. So in this displacement reaction or single displacement or replacement reaction, only a metal higher in the series can displace a one that is lower in the electrochemical series. So that you need it. So we also go to the non-metallic series or the native series, the anions, and see how we can find out reactions that are feasible or not feasible. So for the anions, we have fluoride, SO4, NO3, chloride, bromide, iodide. There are fewer in number compared to the other ones. So you see that. So let's get mnemonics for that. So the reactivity also decreases. Now the most reactive here is fluorine, followed by the sulfate ion, nitrate ion, chloride, bromine, iodide, and then hydroxide ion. If you look at this now, you see that okay, the mnemonics now. So to name it, flying stop will not make sense to you. But if you want to understand how it got the poems, really from the bottom. Those in Britain can never stop flying. Those in Britain can never stop flying. O's in Britain can never stop flying. So O for the OH, I for iodine, B for bromide or Br, C for chloride, N for nitrate, S for sulfate, F for fluoride. But in reactivity, it goes from top to bottom. Now, let's look at this reaction. Chloride plus sodium bromide. Let's see the ones that are feasible here, the one that can take place and the one that cannot take place. So iodide plus potassium fluoride, potassium iodide plus fluorine. So you balance it up. And then perhaps chloride plus sodium iodide, sodium chloride plus iodine. So let's check from the series the ones that are feasible or spontaneous that can take place. They look at this reaction. The non-metal chloride displaces the following non-metal bromine to give you NaCl. they balance it here. Is this reaction possible? Look at the chloride position. Look at bromide. So chloride is more reactive than bromide ion. Chloride is more reactive. So this reaction is feasible because this can displace one. This is weaker. So then look at this one. Iodine displaces fluorine. You can see Ki. So let's look at the study. Look at iodide position at the almost at the end, and fluoride at the top. So fluoride is more reactive than iodine. So iodine cannot display fluorine, but rather fluorine will displace. If here we are to be iodine, fluorine will display iodine. So this reaction is non-feasible because iodine is less reactive than fluorine. Now coming to this one, look at chlorine displacing iodine to have this compound. So chlorine is up here, iodine is down, so chlorine is more reactive. So whether it is for the anions or the cations we studied, is only an element or an ion that is higher that can displace the one that is lower from its compound. It cannot go the other way around. The one lower cannot displace the one that is higher. So when a reaction can take place, when they displace, we say that the reaction is spontaneous or feasible. But if, like in this instance, this one is spontaneous, this one can take place, one can take place, but this one cannot take place. We say this one is not spontaneous or cannot take place. We go to the next kind of reaction called combustion reaction. Combustion reaction on the board is the reaction between a substance. That substance could be an element or a compound with oxygen. So when a substance burns in oxygen, we'll call that reaction combustion reaction. And then this reaction is exothermic because it leads to liberation of heat energy. I can take an element like sulfur, like carbon, plus oxygen give me carbon 4 oxide. It's combustion reaction. I can still take an element like sulfur plus oxygen give me sulfur 4 oxide, which is also combustion reaction. In these reactions, heat energy is always liberated. So we can still have combustion reaction in organic chemistry, whereby hydrocarbons always involved in combustion. In the video we did previously on chemical equation, I used alkanes to demonstrate combustion, like methane. I use methane, butane to demonstrate combustion of hydrocarbons. I can still demonstrate combustion using alkene like 18. You know that alkenes, you can derive their formulas. The formula, general formula CN, where N is the number of carbon atoms, and for alkenes, N starts from 2. The first member, where N is 2, is called 18. Second member, where N is 3, is called propene. Third member, where N is 4, is called butene. Fourth member, in which N is 5, is called pentene. This is the family of alkenes. So if I want to use, let's say, I want to use propene, what I'll do is I'll replace this N with 3. Because for propene, N is 3. C3 H2 times 3, that gives me C3 H6. Then adding it to oxygen. When hydrocarbons bond, they produce CO2 and then water vapor. CO2 and water vapor. So you can balance it. Carbon is 3 here, you put 3 in front. Hydrogen is 6, you put 3 in front to balance hydrogen. That remains is 6. Then going to oxygen, 3 times 2 here is 6. 3 times 1 is 3, that gives you 9 oxygen atoms. But this place you have 2. 9 is not a multiple of 2 because 2 cannot divide 9 unless remainder. So then if you put 4 here, 4 times 2 cannot give you 9. So what do? We divide the bigger number by the smaller value, which is 9 over 2, and put it here, 9 over 2, to make it easy for us. Then what do? We multiply everything with the denominator, which is 2. I open the bracket, you have 2C3H6 plus 9O2 giving us 6CO2 plus 6 water. What did I do? Multiply the coefficients by this denominator 2. So the coefficient here is 1. 1 times 2 is 2. 9 over 2 times 2 is 9. 2 times 3 is 6. 2 times 3 is 6. The equation becomes balanced. You can see the way I did it. I can still use alkynes for that. The alkynes are hydrocarbons with triple covalent bond between 2 hydrogen carbons. So the alkynes have the formula CN H2N minus 2. And N start from 2, just like the alkenes. It's only in alkene that N start from 1. The first member, N is 2, which is called ethyl. Second member, N is 3, which is called propyne. Third member, N is 4, which is called butyne. Fifth member, N is 5, pentyne, and so on. Now let me say I want to use the third member, butyne. So to demonstrate combustion, I'll put C4 H2 times 4 minus 2, replacing N with 4. And I have C4H6. Then plus oxygen, that gives me CO2 plus water. You can see that. So you balance it up. 4 here, you put 4. 6 for hydrogen, and there's 3. 2 here, you put 3. 3 times 2 is 6. Then look at the oxygen. 4 times 2 here is 8. 3 times 1 is 3. 8 plus 3 is 11 oxygen atoms. So let's repeat it. 4 times 2 is 8. 3 times 1, 3, 11. So 11 is not a multiple of 2. So 2 cannot divide 11 unless remainder. So what we will do? Divide 11. Here is 2. Divide 11 by 2. We have 11 over 2. Put it in front there. Then to eliminate the fraction, multiply everything by the denominator, which is 2. Multiply the coefficients. And I have C4, 2C4H6 plus 11 over 2 times 2 gives you 11 oxygen. 2 times 4 gives us 8 CO2. 2 times 3 gives us 6 H2O. So these are examples of combustion reactions, combustion of hydrocarbons. But you have to know, before we go to the next reaction, that combustion of hydrocarbons, whether it is alkane, alkene, or alkyne, follow this formula. So there is a general formula for combustion of all hydrocarbons, which is given as CSHY plus S plus Y over 4 oxygen SCO2 plus Y over 2 H2O. So you want to balance equations involving combustion of hydrocarbons, you can apply the formula on the board. You don't want to balance it by trial and error method. You can use this formula as long as the compound is a hydrocarbon. For example, if I use methane, methane is an alkane, CH4, methane. Instead of balancing it the way I did it before, I can just use this formula. In methane, S is 1, carbon atom is 1 carbon here, and Y is 4. Y is 4 for methane. So I now say CH4 plus S, which is 1, Y, which is 4. 4 over 4, Y over 4. Oxygen giving us S, which is 1, and Y, which is 4. 4 over 2, H2O. So I now have CH4 plus 4 into 4 is 1. 1 plus 1 is 2. That is 2 oxygen now. Giving us CO2 plus, divide this. You have 2 H2O. It says it's a balanced equation. So instead of using the normal way, you know the formula, you can still apply it to balance combustion of hydrocarbons. It's still correct. You can see that. So this is methane. If I choose an alkene to do this, maybe let me choose propene that I used before, and see whether I get the same thing. Propene, which is C3H6. For propene, S is 3, Y is 6. I come here and substitute C3H6 plus my S3, Y is 6. 6 over 4, oxygen giving us S being 3, CO2, Y being 6. 6 over 2 H2O. If I divide, I'll go on to continue working plus 6 over 4. If I divide it, that gives me 3 over 2. And 3 over 2 is 1.5. Add 1.5 to 3, that gives you 4.5 oxygen. Giving us 3 CO2 plus 2 into 6 is 3 H2O. Now I want to clear the decimal, or this fraction here. To clear it, I'll multiply everything by the smallest whole number used to balance, which is 2. So that gives you 2 C3. Multiply the coefficients by 2. 1 times 2 is 2. 2 times 4.5 gives us 9. 2 times 3 gives us 6. 2 times that 3 gives us also 6. So that will become the balance equation. So that is it. Okay. So that makes it simple. We'll go to the next reaction called dehydration reaction. So we now have dehydration reaction. We say this reaction leads to the elimination of elements of water, either partially or completely from a compound to give a new compound. Elimination of elements of water, that means removing hydrogen and oxygen from a compound to give you a new compound. Now, this reaction is very common in organic chemistry. Very common in organic chemistry. Like this compound is called ethanol. Heat, and then this is concentrated H2SO4. This acid is a common substance used in dehydration, and in this reaction, this acid is not called a catalyst, it is called the dehydrating agent. The dehydrating agent. So ethanol heated with this acid gives us ethene and water. So let's look at it from another point of view. For explanation, like ethanol, if I draw the structure, it will look like this: 2 carbon, then hydrogen 1, that is 5 hydrogen, C2H5, and then OH. So I can write this ethanol in a different form, in an expanded form. The first carbon, CH3, can see that? Then the second carbon, CH2, then OH comes in. This is the same thing as the ethanol we're having there. If I want to compress it, I add them together. 1 plus 1 gives you 2 carbon, 3 plus 2 hydrogen gives you 5, and then OH. So if I want to write it in a different form for your understanding, since water molecule is removed. So if you look at this, you can circle off water in this substance written. Water is H2O, so you can remove this. Water is then taken off. What then remains? 1 carbon plus this other carbon gives you 2, C2, and then hydrogen, 3 plus the 1 at the end gives us 4. So water will be removed as H2O. So this equation and this one are the same thing, but this one explains it better. So that is the dehydration reaction, removal of water from a compound or elements of water, hydrogen and oxygen from a compound. This is also another example of dehydration reaction. This acid is called metamoic acid. Metamoic acid. So in this reaction, as you can see, water has been removed. Water is H2O. There's a circle of water. OH and H. So if you bring out 2 hydrogen and 1 oxygen, that becomes water. What remains is CO. Okay? We'll go to the next example. This is called ethane dioic acid, containing 2 functional groups. So remove water, there's a circle of water. You can remove 1 hydrogen here, and then on the other end, you remove OH. So 2 hydrogen and 1 oxygen make up water. What remains? COO is same as CO2. Then CO is carbon 2 oxide. So it's the hydrogen reaction. Look at this one. This is the hydrated salt, copper 2, of a 6 pentahydrate containing 5 water molecules. When heated with this same acid, the water molecule, the water of crystallization will be removed and absorbed by the acid. Look at another example over there. This compound is called glucose. When heated with the acid, we now have the whole water molecules, elements removed, hydrogen, all of them taken off. You can see removed. You now have only 6 atoms of carbon remaining, and then 6 H2O, that is for the water. 6 atoms, 12 atoms of hydrogen, 6 times 2, that is 12, and 6 times 1, 6 of oxygen removed totally. So all these reactions are examples of dehydration reactions. We'll go to the next reaction called double displacement reaction. So we'll now look at double displacement or replacement reaction. We say this is a reaction in which 2 ionic compounds exchange their ions to produce 2 products. The products could be in any of the following form. The products could be an insoluble compound known as a precipitate, could be a molecular compound, example water. The product could also be a gas. So this is the general nature of double displacement reaction. So let's look at the first example. The product could be an insoluble compound. For example, look at this reaction: sodium chloride plus, let me say, silver triazonitrate 5. In this reaction, we have silver chloride produced plus sodium nitrate produced. So, balancing the equation. Where is balance? I think it's already balanced. Yeah. So, if you look at this, solid and then aqueous. So, if you look at that, you see a reaction, double displacement reaction. In this reaction, we have two reactants, ionic compound salts, ionic because this can ionize into sodium ion, chloride ion, silver ion, and then nitrate ion. There's a change of ions or a change of radicals. That's what happens here. So this one picks this one to form that. This one picks this one to form that. Out of the products formed, one is a solid, the other one is a aqueous. So this solid formed is called the precipitate. So the solid formed during a double displacement reaction is called a precipitate. So that is this reaction is of course called this reaction in which two solutions meet to form one solid, and the solution is called precipitation reaction in chemistry. So precipitation reaction is an example of double displacement reaction. So precipitation reaction is one of the examples of double displacement reaction, whereby two ionic compounds come together to produce one solid and one solid means one insoluble compound and an aqueous solution, aqueous compound. So two soluble, so I say insoluble plus soluble, producing insoluble plus soluble. The insoluble one form is called a precipitate. So that is what is meant by a precipitation reaction, which is an example of double displacement reaction. That explains formation of insoluble product. So double displacement reaction can lead to formation of insoluble compound, and that insoluble compound formed in that reaction is called a precipitate. Okay, now if you are given this question, you have this. Let's go back to that equation that we use. Silver nitrate plus sodium chloride plus silver nitrate, then silver chloride, and then sodium nitrate. You now ask, which of the substances, this substance here, I call it the precipitate because it's the insoluble substance or product formed during when you mix two soluble compounds or during double displacement reaction. And you ask, which of the reactants is the precipitating agent? The precipitating agent. Precipitating agent is different from precipitate. Precipitate is a product, the insoluble product. But precipitating agent will be one of the reactants. They ask you, which of them is the precipitating agent? The precipitating agent in this reaction is sodium chloride. Sodium chloride. So how do you find out the precipitating agent? Look at the precipitate. The precipitate contains a positive ion, silver, and another ion, chloride. Now you ask yourself, these two ions are being contributed by the reactant. This silver came from this one, this chloride came from this other reactant. The reactant that contributes the negative ion in the precipitate, the chloride ion, is called the precipitating agent. So precipitating agent usually contributes the negative ion or the anion to the precipitate. So that's why this is the precipitating agent. Let me take another example. Assuming that we have, let's say, lead nitrate, aqueous, under precipitation reaction, have lead sulfate, and then HNO3. So if you look at this reaction is a precipitation reaction because if you look at it very well, you see that two soluble compounds have combined. How do I know the soluble compounds? The aqueous state shows solubility, soluble in water. Produce one soluble and one insoluble. So this one is the precipitate produced. Then which of the reactants is the precipitating agent? Look at it very well. You see that if you break this into two, Lead-2 and SO4 negative radical. So this came from H2SO4. So the H2SO4 now functions as the precipitating agent. So that explains precipitation reaction and the key terms we use in precipitation reaction, which is precipitate and precipitating agent. Demonstrating precipitation reaction is an example of double displacement reaction. Another example is a reaction in which we have water produced. Another example of a double displacement reaction is the one we call neutralization reaction. Neutralization reaction, which is the reaction between acid and base, is also another example of double displacement reaction. For example, HCl plus sodium hydroxide, water is produced. Hydrogen acid split into anion and chloride. This one split into sodium ion and hydroxide. When online terms together, you produce sodium chloride and then water. Water produced as one of the products. So you see that there's a double replacement or displacement. This one displaces, sodium displaces hydrogen, chlorine displaces hydroxide. So this is also double displacement reaction, but it is regarded as neutralization reaction also. So we are seeing two reactions that can be classified as double displacement reaction. We are seeing precipitation reaction. We are seeing neutralization reaction. Another example of a reaction that is also classified under double displacement reaction is the reaction that leads to gas production. For example, iron sulfide plus HCl giving us iron chloride and a gas called hydrogen sulfide. So this reaction is also called double displacement reaction. You can see it very well. So normally, this reaction normally involves two reactants. In all the examples we're taking, two reactants and two products. So iron 2 sulfide, hydrogen ion chloride. So there's a change of radicals or replacement of radicals. Iron 2 chloride, hydrogen sulfide. This one is a gas. So this is also a double displacement reaction in chemistry. About the rules guiding insoluble salts in chemistry or insoluble compounds in chemistry, you can go through our videos or on solubility. Go stream our videos with this solubility for O-level students. And then in that you're going to see rules guiding solubility of compounds. Then you can be able to listen to the video, watch it very well, and then the guideline we gave there. So that guideline, you see the list of how to know soluble compounds and how to know insoluble salts. So insoluble compounds in chemistry. Like we know that all common salts or group 1 elements, all sorts of sodium, potassium, lithium, rubidium, all sorts of group 1 elements like sodium chloride, sodium nitrate are soluble in water. You should know that all nitrates are also soluble in water. All hydrogen carbonates are soluble in water. All sulfates are soluble except lead sulfate and barium sulfate. Just go to the video. All chlorides are soluble in water except silver chloride, lead-2 chloride, mercury 1 chloride, copper 1 chloride. These ones are the ones that are insoluble. All carbonates are soluble in water, insoluble in water except those of group 1 and that of ammonium carbonate. So if you go to the video, you can be able to know the rules so you can know when to put S. If I put S, don't put the S by mistake. When we put S, like when we see this kind of salt and we put S, we know that this salt is insoluble. When we see this and put S, we already know from that rule I listed that this salt, silver chloride, is insoluble in water, and so on. So we'll go to the next reaction called redox reaction. So redox reaction, we'll have it on the board. We're going to take a brief explanation of this reaction because the reaction is more complex as we'll have it on the board. So it should be a different topic for another day. But let's look at what the basic concept of this reaction. By definition, redox reaction, that red is an acronym. So that red implies reduction for red, oxidation for us. So redox means reduction, oxidation reaction. So redox reaction or reduction oxidation reaction is defined or is a reaction that leads to electron transfer and change in oxidation states of elements. I want to talk about redox reaction, the important key concepts we have to understand. Oxidation. What's oxidation? There are different ways to define oxidation, but we're taking some few definitions here. Oxidation is the electron loss or process of electron loss, or you can say oxidation is the increase in oxidation number of an element. Reduction is the process of electron gain or the decrease in oxidation state of an element. Oxidation agent is the reactant whose oxidation state decreases or the reactant that has been reduced. The reducing agent, the reactant whose oxidation state increases or reactant that is oxidized. So we're going to take some few examples here. As I said, the topic is very broad. We'll have to do it or everything today. We'll do as much as we can carry on in this video. So having done that, let's take some few examples. For example, let's say we have a reaction of this nature, 2Fe plus chlorine giving us 2FeCl3. So this reaction is a redox reaction. So let me ask you, why is it a redox reaction? Because you're going to look at the oxidation states of the elements in this reaction. Let's start. Chlorine, any element on its own, for example, you have element uncombined on its own in a reaction, or as a molecule, without combined with another element, is on its own. We take the oxidation number as 0. So the oxidation state of chlorine is 0 here because chlorine is not combined with another element. Then coming to this one, the oxidation state of chlorine here in binary compound. Binary means a compound of two elements. Halogens maintain oxidation state of -1. Be chlorine, fluorine, bromine, iodine of -1. As long as the compound contains only two elements. But the compound contains three elements, like in this situation now. This is not binary. Halogen cannot maintain -1. We calculate it to get the oxidation state of the chlorine. It's different from in this. So in binary compounds, halogens maintain -1. Also, this is binary, -1 for chlorine. Having seen that, now look at ion. How we get the oxidation of ion here? All you have to do, you equate the compound to 0 and calculate ion. Call ion S, unknown. Then chlorine, which we say is -1, determined from the rules, then oxidation state. So now S minus 2, 0, S becomes equal to 2. So ion here is +2 state. For this one, also calculate it. FeCl3 equal to 0. Call ion here S, chlorine also -1, being a binary compound. 3 times -1, so S minus 3 is 0, S plus 3. So +3. So why is this reaction considered as a redox reaction? Because there are changes in oxidation state. Ion had changed from +2 to +3. Increment. Meaning that this compound has been oxidized. Increase the number is oxidation. This compound has been oxidized. Ion 2 have been oxidized. Because ion have moved from 2 to 3. Why chlorine, this reactant, has been reduced? Because chlorine has moved from 0 to a smaller number, which is -1. So this has been oxidized. This one has been reduced. Oxidation occurring here, reduction occurring on this one. That's why it's called a redox reaction. So these rules, you have to master them and know them. Take another example of a redox reaction to explain what is meant by oxidation and redox. Let's say, let's look at this one, H2S plus SO to give us water and sulfur. So whether it's balanced or not may not matter here anyway, but let's try to balance it. Okay, 3. So why is this one a redox reaction? Look at it. In compounds of hydrogen, where hydrogen is bonded to a non-metal, or especially when hydrogen is the first element, when hydrogen is the first element in a compound, we give it oxidation number of +1. Then you may not know that of sulfur. If you're not sure that of sulfur, you equate the compound to 0 and calculate sulfur. Since you know this one, 2 times 1, call sulfur S equal to 0. S equal to -2. So sulfur here is -2. Okay? You come to this one. So that means for you to calculate the state of one element in a compound, you must know one of them. If there are 3 elements, you must know 2, and then the middle one, you find it. So there are 2 elements here. We must know one to find the other. Oxygen is always -2 in most compounds. -2. So you may not know sulfur. Sulfur, because sulfur is -2 here, does not mean it should be -2 here. Sulfur is one of the elements that changes oxidation state regularly in compounds. So to get sulfur here, I'll equate to 0 and calculate sulfur. So call it S, oxygen is minus 2 times 2, 0. So S minus 4, 0. S gives us plus 4. So here it becomes plus 4 for sulfur. Move to this. Hydrogen maintains constant state when it's in front as plus 1. Oxygen always maintains minus 2. So the elements that have constant state. Then sulfur on its own, because it's not combined with any other element, the state is 0. As I said, when I use chlorine example, when element is on its own, we take the oxidation state as 0. So let's see, why in the redox reaction, hydrogen moves 1 to 1, no change in hydrogen. What of sulfur? Minus 2 to 0. The state of sulfur has increased from minus 2 to 0. So this one is higher, 0 is higher than minus 2. There's a change in oxidation number. This compound has been lifted. So this compound is oxidized. So for sulfur here, I move from minus 2 to 0. Coming to this one, oxygen is minus 2, minus no change. But what of the partner? Plus 4 here, 0. So the state of sulfur here has reduced. So this compound has been reduced. So don't expect the two elements to have change in state. But one of them changes, that is okay. So oxygen did not change, but sulfur changed or decreased. Hydrogen did not change, but sulfur also here increased. These have been oxidized, going from minus 2, going higher. While this one has been taken down, going lower. This one from 4, these have been reduced. So this is the redox reaction because there are changes in oxidation state of the elements concerned. So as long as there are changes in oxidation state, that reaction is classified as a redox reaction. And the example, maybe we have copper plus H2SO4 giving us copper sulfate plus water plus SO2. Let's find out whether this reaction is a redox reaction. Copper is 0 here because it's on its own, a free element, not combined with another element. And I told you, in compound that involve hydrogen, hydrogen the first element is given plus 1. It has a constant state. Oxygen also has a constant state of minus 2. The one we're confused with is the middle one, sulfur, what to give it. What to do is we equate the compound to 0 and calculate sulfur. Don't use this to just use the formula of the compound. So replace hydrogen with 1, sulfur unknown, oxygen minus 2 equal to 0. So now I have 2 plus S minus 8, 0. 2 minus 8 is minus 6. So S is 6. Sulfur there is plus 6. That's why it's called the dose sulfur 6. In SO4, sulfur is always 6. Coming to this one now, oxygen is minus 2 in compounds, unless it's on its own. When it's as a free molecule on its own, we'll take it as 0. But in a compound, it must have oxidation state. Copper is 2. Then in SO4, sulfur is plus 6, as the same thing here, SO4 plus 6. Coming to this one, hydrogen is 1. Good, because it's the first element combined with a non-metal. Oxygen is constant, which is minus 2. Coming to this one, so oxygen is minus 2, which is oxygen has a fixed oxidation state. In almost all its compounds is minus 2. They set in peroxides. Then sulfur here, SO2 equal to 0. S plus minus 2 times 2, 0. S equal to 4, crossing over, plus 4. So having done that, now copper has gone from 0 to increase. So that means this copper has undergone oxidation, 0 to plus 2. Then hydrogen is 1, no change for hydrogen. Let's look at other elements. The oxygen is minus 2, minus 2, minus 2, no change for oxygen. But what are the elements there? Sulfur is 6 here. Here is 6. Is there any place we have sulfur? Yes. Here is 4. So from 6 to 4, this compound have been reduced because it's sulfur that brought about the change, even though the other ones are constant. Sulfur decreased from 6 to 4, but here copper increased from 0 to 2. This compound have been oxidized, so this is a redox reaction. So as long as there is changes in oxidation state of one of the elements when you're moving from left to right in each compound, that reaction is a redox reaction. But if there is no change at all, that means it is not a redox. For example, look at this reaction. HCl plus sodium hydroxide giving us NaCl plus water. Look at this reaction, which is a double displacement reaction or neutralization reaction. Hydrogen here is plus 1 because it's the first element we're seeing here. Or you combine with a negative element. So in binary compounds, as I told you, compound of 2 elements, halogens maintain -1. Then sodium, the oxidation of sodium, group 1 elements have constant oxidation state. Sodium is +1. Oxygen -2. Hydrogen +1 bonded to a negative element. Sodium group elements maintain their group number as their position state. Binary compound, halogen become -1. Or you can calculate if you wish. So you know this is 1, this is unknown. Then calculate S. S is -1, S become, that is for the halogen. Then hydrogen +1, oxygen -2. Look at hydrogen +1 here. Go to the other side, +1. Chlorine -1 here, the other side -1. Sodium +1 here, the other side +1. Oxygen -2 here, the other side -2. Hydrogen +1, the other side. So there's no change at all. That means this reaction cannot be called a redox reaction. You can see that. How to find out whether a reaction is a redox reaction or not. So when you have redox reaction, there must be a change in oxidation state. Now, having done that, there are some rules you should know. Oxidation state of oxygen is always -2 in compounds. Like in compounds, or have -2. You can then calculate copper. If you're not sure, but you put it into 0 and calculate copper, say S plus -2, but then S becomes +2. In compounds that have oxygen is always -2. Maybe except in peroxide where they have -1. Then oxidation state of hydrogen, when it's bonded to a non-metal or when it's in front, is always +1. That's the rule. You have to know this. That will help you to facilitate your calculation. Oxidation state of group 1 elements. Group 1 elements like sodium, potassium, francium, lithium is always +1 in compounds. But when they're on their own, like in this case, in this case, they are not in compound, they are free. We now take them as 0. Oxidation state of group 2 elements like calcium, magnesium, barium in compound, I did not say on their own, is +2. When they are on their own, like in this case, we take them as 0. But in compound, like in sodium chloride, or in this one now, is a compound, this is +1. In calcium chloride, this is +2 because in compounds. Then for group 3 elements, oxidation state of group 3 elements in compounds, like aluminium, boron is also +3. But when they're on their own, that is reacting as a free element, we take them as 0. So that will help you to understand oxidation number very well. When elements on their own, they are not found with other elements, they're not in compounds. They're either as molecules or elements. We take the oxidation state as 0. Then oxidation state of halogens. Halogens are fluorine, chlorine, bromine, iodine, is -1 in binary compounds. Binary compounds are compounds of 2 elements, like sodium chloride, potassium bromide, sodium fluoride. So in this case, they're all -1. You should know that. But on their own, we'll take them as 0 when they are not combined with element, when they're writing in this form. But when they are in non-binary compounds, so non-binary compounds, we cannot take their state as 0. For example, look at this one, NaCl. This is 3 elements, 1, 2, 3, non-binary. So the source of chlorine here cannot be 0, it's going to be positive. So let's see how to get it. We equate to 0 and calculate it. Sodium is group 1, 1. Chlorine is unknown, which are looking for S. Oxygen is always -2, -2 times 3. So we want to find chlorine. Now 1 plus S minus C is equal to 0. So S, 1 minus C is -5, 0. S becomes +5. So chlorine here now is +5 because it's a non-binary compound. I did not say it's +5 always. You can switch to another value, but definitely cannot be -1 in non-binary compound. That is for halogens. So get that in mind and then be able to go through oxidation state very well, or redox reaction very well. So we have some exercises on the board, some miscellaneous questions on the board. We asked to classify the following reactions. So let's go through them one by one and then give the answers. For the first one, you have 2 reactants, 2 elements forming 1 compound. Which reactions involves two or more elements to give you only one product? So the first one is called combination reaction or synthesis reaction. That's the first one, the answer to the first one. Second one, you see a compound splitting into two or more products. Which reaction might involve a compound to give you two or more products is called decomposition reaction. But the initiator or the agent that brought about is light, UV rays. So this is called photochemical decomposition reaction because of the agent involved here. Number three is more like number two, whereby one reactant split into two or more, three products, one, two, three. One reactant splits into more than two products using heat. So this reaction is also decomposition reaction, but because heat is the initiator, we now call it thermal decomposition reaction. Going to number four, you see this substance is bonded with oxygen. So oxygen with methane giving you this. So this reaction is combustion reaction. We're going to number five. An acid and an alkali giving us salt and water. Acid and base, salt and water. So this is called neutralization reaction, or you can call it double displacement reaction, whereby potassium displaces hydrogen, took its position, and then SO4 displaces hydroxyl to give us, potassium displaces hydrogen, or we'll put it this way, potassium here displaces hydrogen, and then hydrogen then join to OH giving us water. So it's double displacement, or you can still call it neutralization reaction. Going to number five question. Look at the state. This is the salt, aqueous plus a gas, giving us a solid and aqueous. This solid, this is also double displacement. So like here, lead pick sulfur, while hydrogen pick nitrate to give you this. So double displacement. But actually, we'll call it precipitation reaction because we have a solid. One of the products is a solid, which is a precipitate. Going to number seven reaction. Number seven looks somehow. Number seven reaction is also called double displacement. Number seven has two names. There are two reactions in number seven. Number seven is acid and carbonate. So the reactions there are double displacement reaction and decomposition. So two reactions took place in number seven. The major one is double displacement followed by decomposition. Mind you, double displacement is also called double replacement. So why did I say so? Look at the reaction. Let's analyze it. Plus HCl. So this splits into sodium and then carbonate. This splits into hydrogen ion and then chloride. Marry online terms together. You have sodium chloride. You have H2CO3 by balanced HCl. The 2 goes to hydrogen. That's why you have this. But the product we have there is CO2 and water, not H2CO3. When I taught you chemical equations, I told you that this acid is unstable. I mentioned three compounds that are unstable. I mentioned this one. I mentioned also H2SO3. I also mentioned NH4OH that split when they are produced. So this split into water and then CO2. So you have that. So the first reaction that took place here is double displacement, where the ions exchange each other. Double displacement. And then decomposition, because one of the products then decompose afterwards. So there are two reactions here. The first, double displacement, and then decomposition taking place. Going to number 8. Number 8 is also double displacement and decomposition reaction. Check it very well. You can see K2SO3 plus HCl. We now have potassium and then SO3, hydrogen and then chloride. On light terms interchange, you have potassium chloride. Then bring this together, you have H2SO3. But the product we have on that is H2O and SO2. What happened is one of the compounds we say that can decompose. You can see it there. It gives you water and then SO2. So the reaction is similar to the above, to number 7, which is double displacement and decomposition taking place. Reactions taking place. So the two reactions are similar to each other. So having done that, we have done justice to our today's program or work on general chemistry for first year students. Stay connected as we bring you instantly the other part, that the objective part of this topic. Now go over to the multiple choice part of this topic. Number 1 says, which of the following is the characteristics of a chemical reaction? A. The composition of the substances remain unchanged. B. Energy is absorbed or released. C. Only physical changes occur. D. The total number of molecules remain constant. The answer to this question is B. Energy is absorbed or released in chemical reactions, whereby if it is absorbed, we say we have endothermic. If released, we say we have exothermic reaction. Number 2 says, what is the correct term for a reaction where a single compound breaks down into 2 or more simpler substances? A. Synthesis reaction. B. Decomposition reaction. C. Combustion reaction. And D. Single decomposition reaction. The answer to the question is decomposition reaction B. Number 3, we look at that equation between hydrogen molecule and oxygen giving us water. It said, what type of reaction is represented above? A. Synthesis. B. Combustion. C. Single displacement. And D. Decomposition reaction. The reaction above can be classified as combustion reaction because hydrogen is burnt and also gives us water. Option B is correct. Number 4 says, with the following example of redox reaction: A. Sodium chloride breaking into sodium ion and chloride ion. B. Hydrogen combined with oxygen giving us water. C. HCl plus sodium hydroxide giving us sodium chloride and water. D. Calcium carbonate plus calcium oxide giving us calcium carbonate decomposing to calcium oxide and CO2. The answer is B. The answer is B. Why is it B? So the answer is option B, because in redox reactions, you should observe changes in oxidation number. You can see the solution there. Hydrogen in a molecular state on its own without being combined with another element, the oxidation state is 0. Likewise, oxygen. But at the product side, the two elements are combined. Hydrogen maintains +1 when bonded to a electronegative element like oxygen, and oxygen maintains -2. So that the hydrogen has changed from 0 to +1, and oxygen has changed from 0 to -2. So hydrogen has been oxidized and oxygen reduced. So the answer is B. Number 5. A reaction in which one element displaces another element is in a compound is called A. Double displacement reactions. B. Synthesis reaction. C. Single displacement reaction. D. Redox reaction. The answer is single displacement reaction, option C. Number 6. The following example of combustion reaction: hydrogen decomposing to hydrogen and water. So A is decomposition reaction. B is methane and oxygen giving us CO2 and water. So B is the combustion reaction. Answer is option B, because C is double displacement and D is either synthesis or redox reaction. So the answer is B, combustion reaction. Number 7. Which of the following is not a characteristic of an exothermic reaction? A. Energy is released. B. The products have a lower energy than the reactants. C. Heat is absorbed from the surroundings. And D. The reaction feels warm to touch. The answer is C. Heat is absorbed, because in exothermic reaction, heat is given out, not absorbed. So option C is the answer. Number 8. Which of the following is an example of double displacement reaction? I see the equations there. The answer is option A. 2 reactants and 2 products. So you can see A is double displacement. In A, sodium displaces silver to take nitrate, while silver 2 chlorine to give you silver chloride. So this is a double displacement reaction. Number 9, the reaction sodium plus chlorine giving us sodium chloride is an example of A. Synthesis reaction. B. Decomposition reaction. C. Single displacement reaction. And D. Combustion. The answer is synthesis, because sodium and chlorine are 2 reactants combining to give you only 1 product. 10. A catalyst in a chemical reaction: A is consumed in the reaction. B speeds up the reaction by lowering the activation energy. C changing the equilibrium constant of the reaction. D. Increase the temperature of the reaction. The answer is option B. Speeds up the reaction by lowering activation energy. Number 11. What is formed when an acid reacts with a base in a neutration reaction? A. Water and salt. B. Water and a gas. C. Water and a metal. D. Salt and a gas. The answer is water and salt. 12. What type of reaction is represented by the equation hydrogen peroxide, giving us water and oxygen? A. Synthesis reaction. B. Combustion. C. Decomposition. And D. Displacement. The answer is decomposition reaction, which involves one reactant, two or more products. 13. In the reaction between zinc and hydrochloric acid, which element is oxidized? A. Zinc. B. Hydrogen. C. Chlorine. And D. Oxygen. The answer is zinc, option A. So let's go through and explain why through the question. So let's explain it. In a redox reaction, the soft element oxidized must be a reactant and never a product. So the answer cannot be any of the product. So it should be a reactant. And the oxidized element is that element whose oxidation number increased from left to right. Look at zinc, 0 on the right hand side. Look at zinc on the product side, +2. So from 0 to +2 is an increment. So zinc, the reactant whose number increases, is the one that oxidized. Zinc is +2. Then let's check the other ones. Hydrogen in HCl is +1. Chlorine is -1 because that compound is the binary compound of halogen. That is a compound of two elements in which halogen is found, as explained before. Then let's go to the product. In zinc chloride, is a binary compound also of halogen. Chlorine is -1. Can calculate zinc, equate the compound to 0, making chlorine -1 and replacing zinc with S. Can look at the calculation. S plus -1 times 2 equal to 0. S minus 2, 0, then S is 2. So zinc is +2 there. Then hydrogen is 0 because it's on its own. It's not combined with any other element. So if you check all the sides, hydrogen is +1 here. On the other side is 0. So from +1 to 0, hydrogen has been reduced. Chlorine -1 on the HCl. In zinc chloride -1. So chlorine is neither oxidized nor reduced. So the one that's oxidized is zinc, whose value increases from 0 to +2. Number 14. A reaction where two or more reactants combine to form a single product is called. Two or more reactants giving us a single product is called A. Decomposition reaction. B. Combustion. C. Synthesis. D. Single displacement reaction. The answer is synthesis reaction, where two or more reactants form a product. The answer is option C. Number 15. In a chemical reaction, the reactant that is completely consumed is called the A. Limiting reagent. B. Excess reagent. C. Catalyst. D. Solvent. The answer is limiting reagent. Limiting reagent is the one that is consumed completely during a chemical reaction, while the one that remains after the reaction is called the excess reagent. Number 16. The reaction between zinc and copper sulfate, giving us zinc sulfate and copper, example of A. Combustion reaction. B. Synthesis reaction. C. Single displacement reaction. And D. Double decomposition reaction. That reaction given above is example of single displacement reaction, option C. If you look at it, zinc has replaced copper, giving us zinc sulfate, and then copper coming out in place of to take the position of zinc. So that is single displacement reaction. So now we're going to go over to some questions involving chemical equations, the first topic that we did. Number 1 says, which of the following is correctly balanced equation for the reaction between nitrogen and hydrogen gas to form ammonia? We have the different options. So the reactants are nitrogen and hydrogen in the equation, and then the product is ammonia that is being formed. So let us balance it and then check the options. So we see the equation between the two reactants, hydrogen and nitrogen and hydrogen, giving us ammonia. We'll draw a table as you are taught in the class in the first video. Elements, nitrogen and hydrogen, left hand side and right hand side. You count the atoms. How many atoms of nitrogen on the left hand side? 2. How many of hydrogen on the left hand side? Also 2. So write them down, giving us 2, 2. Go to the product. How many of nitrogen is 1? How many of hydrogen is 3 atoms of hydrogen? So we inspect the table and we'll see that the two elements are unbalanced. So which of them will be easier to balance? It's going to be nitrogen. We're going to multiply 1 by 2. Multiply by 2 here. So having done that, so we'll increase nitrogen on the right-hand side. We'll go to the equation and put 2 in front of nitrogen. Having done that, we'll change the table for the right-hand side because that 2 will also affect hydrogen. Hydrogen now becomes 6. So hydrogen becomes 6 times 2 here, that is 6. So we'll go back to the table and then we'll see that nitrogen is balanced, remaining now nitrogen. Nitrogen is balanced 2 to remaining hydrogen. Hydrogen is 2 on the left-hand side and 6 on the right-hand side. So what do we do to hydrogen? 6 is a multiple of 2. So to balance this side, multiply this side by 3, giving us 6. So locate hydrogen and put 3 in front of it on the left-hand side. So this is a balanced equation between the two. 1 molecule of nitrogen, 3 molecules of hydrogen, and then 2 molecules of ammonia. So the answer is option A. That's the right answer to the question. Go to number 2. You have methane plus oxygen giving us CO2 and water. And we ask what the coefficient of oxygen in the balanced form of the above equation. Option A 5, B 13, C 2, and D 10. So we're going to balance the equation first. So try to balance the equation. Look at carbon on butane. 4 atoms will have 4 atoms of carbon there. On the right hand side, we'll have 1 of carbon. We'll put 4 in front of CO2 to balance carbon. We'll go to hydrogen. We'll have 10 there on the left hand side. On the right hand side, we'll have only 2. To balance hydrogen, we need 5 in front of water because 5 times 2 is 10. Remaining oxygen. So oxygen here in CO2, 4 times 2 is 8. 5 times 1 is 5. So 8 plus 5 give you 13 oxygen atoms. While on this side, we have only 2 oxygen atoms. And you see that 13 is not a multiple of 2. So divide 13 by 2 and place it over there, 13 over 2. That is it. Then we'll multiply everything by the divisor, by the denominator, that is 2 under 13. That gives us 2C4H10 plus 13 oxygen, giving us 8 CO2 plus 10 H2O. So the coefficient of oxygen is 13. That's the number in front of oxygen in the balance equation is 13. So the answer to number 2 is option B, 13. Go to number 3. You say, what the coefficient of water in the balance equation for combustion of propane? Option A, 3, B, 4, C, 5, and D, 8. Coefficient of water. So we have to balance the equation and get the answer. So to balance the equation, we have to check the equation very well. The right-hand side contains 3 atoms of carbon. Product side contains only 1 atom of carbon. So we have to put 3 in front of CO2 to balance carbon. Having done that, let's look at hydrogen. There's 8 atoms of hydrogen on the reactant. Product only 2. We put 4 in front of hydrogen to balance hydrogen, that is 8. We check oxygen. Oxygen in CO2 have 3 times 2, that is 6. Then another one, 4 times 1, that is 4. 6 plus 4, that gives us 10 for oxygen. So that is it. On the other side, you have 2. And luckily for us, 10 is the multiple of 2. So 2 can divide 10. 2 into 10 is 5. So all we need here is 5. And we're looking for the coefficient of water. The answer is 4. 4. That's the number of moles of water. So the answer to number 3 is option B. Looking at number 4, they say balance the equation and find the coefficient of ion. The relation is between ion and oxygen to form Fe2O3, ion 3 oxide. Option A, 1, option B, 2, option C, 3, and option D, 4. So let's balance the equation. Look at the equation there, written again from the question paper. The elements are the symbols ion and oxygen. Ion is 1 atom, oxygen is 2 atoms on the left hand side. Product side, ion is 2, oxygen is 3. So none of them is balanced. And the one that be easier for us to balance first is ion by multiplying 1 by 2. Go to the product's right hand side, left hand side, and put 2 in front of iron. When we are done that, then we have to now contemplate on what to do with oxygen. So oxygen, if you look at oxygen, we have 3 atoms here and 2 there. And on the right hand side, the oxygen is smaller, and oxygen, look at the equation, oxygen is on its own. So whatever number we put in front of it will only affect oxygen. It's then that we now apply fraction. You apply fraction when you have one element remaining and that element is on its own. So whatever number you put on it will only affect it. So what do? Since 2 is not a multiple of 3, we divide the bigger number by the smaller, is 3 over 2, what to use now, and put in front of oxygen, 3 over 2. So since we don't normally balance with fractions, we remove the fractions by multiplying everything by the divisor of the fraction, which is 2. So multiply everything by 2. We now have 4Fe plus 3O2, 3 over 2 times 2, plus 2Fe, 2O3. So the coefficient of oxygen here is 3O2. So in the equation, we are asked the coefficient of iron, not oxygen. So the coefficient of iron here is 4Fe. So our answer to the question is option D, 4. Number 5 says, what is the coefficient of oxygen in the balance equation for the decomposition of potassium chloride? We had that equation given to us there. We're asked to find the coefficient of oxygen, option A, 2, B, 3, C, 6, and D, 4. So let's go and work it out. So we can see the equation there, and then the table drawn, elements, the symbols listed for us, potassium, chlorine, oxygen. The left-hand side contains 1 atom of potassium, 1 of chlorine, and 3 of oxygen. Right-hand side, 1 of potassium in potassium chloride, 1 of chlorine, and 2 of oxygen. If you examine the table very well, you see that all the atoms are balanced except oxygen. Which side of oxygen is smaller is the right-hand side, the product side. So go to the product side and look for oxygen. Is it on its own? Yes, you can see oxygen on its own. So we can apply fraction. Since 3 is not a multiple of 2 and oxygen we're looking for is on its own, we divide the bigger number 3 by 2 and then move it to the front of oxygen 3 over 2. When we are done that, then to clear the fraction, multiply everything by 2. That gives you 2KClO3, giving us 2KCl plus 3O2. So the coefficient of oxygen is 3 in this balance equation. So for number 5, the correct answer is option B, 3. Number 6 says, balance the following equation and find the coefficient of CO2. So that equation, the combustion of hydrocarbon called hexene plus oxygen, giving us CO2 and water. Option A, 6, B, 5, C, 4, and D, 3. We want to look for the coefficient of carbon 4 oxide. So let's work it out. So balance the equation, carbon is 6 on the left-hand side and 1 on the right-hand side. So we append 6 in front of CO2. And then hydrogen is 12 on the left-hand side. And then 2 on the right-hand side. To balance it, we need to put 6 in front of H2 because 6 times 2 is 12. Then we'll find oxygen atoms. On the left, 6 times 2 is 12. 6 times 1, 6. So 12 plus 6 is 18 oxygen atoms on the left-hand side. Then on the right-hand side, we have only 2. So 18 is a multiple of 2. So do 2 into 18 is 9. So what you have in front of us is 9. So 9O2. So the coefficient of CO2 in this reaction is 6. The number of CO2 is 6. 6 molecules of CO2 produced. So number 6, the answer is option A, 6. Number 7. Which is the balance equation for the reaction between aluminium and oxygen to form aluminium oxide? Aluminium and oxygen to form aluminium oxide. So let's work it out. So solving it, aluminium is Al, a symbol. Oxygen is O2 because it's diatomic. So I have to put 2 on it. So to get a product, the valency of aluminium is 3. Number is 13. To write the electronic configuration is 283. 2 in the case shell, L shell 8, and then that is that. That means a metal. And then a metal, the valence of metal is what you have in the outermost shell, that is 3. Then take only one atom of oxygen, that is O. The atomic number of oxygen is 8. That is 2, 6. In the atomic shell has 6. So oxygen is the non-metal because it has more than 3 in the last shell, has 6. It's non-metal. And non-metal, the valency is not what you are seeing in the atomic shell. The valency is how many they were set to make it up to 8. So subtract this 6 from 8. That gives you 2. The valence of oxygen is 2. So the formula of the compound form is obtained by a changing valency. 3 for aluminium goes to oxygen, and 2 from oxygen goes to aluminium, which is 2Al2O3. So we're going to have Al2O3. So we'll balance it now. To balance it, what do? We'll draw a table and then write out aluminium, oxygen. On the left-hand side, aluminium is 1, oxygen is 2 atoms. Right-hand side, aluminium is 2, oxygen is 3 atoms. We inspect the table and balance. So the side, we're going to balance aluminium that faster. So to balance this smaller side, multiply it by 2, the left-hand side. So place 2 in front of aluminium. You see that? So we balance aluminium, remaining oxygen. To balance oxygen is not easy because 2 is not a multiple of 3. What then do? We ask ourselves which side of oxygen is smaller. Is on the left-hand side. We check whether oxygen is on its own. Yes, it's on its own, so we can use fractions. So what do? Divide the bigger number 3 by 2. So that is it. We're going to put it in front of the oxygen there. When we have done that, we'll remove the fractions, multiply everything by the